Hello everyone. Today, I, Anand Choudhary from BTech Engineering Physics 3rd year would be presenting a case study on a physiological control system. Specifically, I would be talking about the linearized lung mechanics system. To start with, let us briefly discuss and examine some parameters pertaining to the human lung which would help us in building the linearized lung mechanics model. The airways in humans are divided into two categories. Number one, the large or the central airways, which start from the trachea and extend right up to the end of the bronchi, and the small or the peripheral airways, which start from the bronchioles and extend right down to the alveolar sacs or the alveoli. We would be denoting the pressure at the airway opening by PAO, the pressure in the central airways by PC, and the pressure developed in the alveolar sacs by PA. Furthermore, the human lungs are covered by a protective thin layer of tissue that is essentially a double layered tissue referred to as the pleura, and the pressure that develops in between the two layers of the pleura, that is the parietal pleura, which covers the interior wall of the chest cavity, and the visceral pleura that is directly going to cover the lungs is going to be denoted by PPL, that is the pressure in the pleural space. With these quantities defined and at our disposal, we can now define the linearized lung mechanics model. We consider an electrical circuit-based model of linearized lung mechanics. Whenever air enters the human airways, it is essentially the flow of air is going to be resisted by the central and the peripheral airways, and this resistance is accounted by the inclusion of two fluid mechanical resistances, namely the central airway resistance RC and the peripheral airway resistance RP. The air that enters the alveolar sacs in humans is also going to produce an expansion of the chest wall cavity by the same volume. This fact is represented by the inclusion of a series connection of the lung and the chest wall compliances, that is CL and CW respectively. Essentially, compliance is the mechanical analog of capacitance that essentially denotes storage. So here we are talking about the storage of air. At the same time, furthermore, we note in this particular system itself, we have already considered the cases of CL and CW. Now we note that the air that enters the respiratory system, a small fraction of it is shunted away from the alveolar sacs, that is the alveoli, and that is because of the compliance of the central airways and the gaseous compressibility. And this fact is represented by the inclusion of the compliance of the central airways, that is the shunt compliance. So this is the compliance of the central airway CS that is connected in shunt with the series connection of CL and CW. Now Q represents the volume flow of air that is entering the respiratory system when PAO is the pressure in the airway opening, and QA refers to the volume flow of air that is delivered to the alveolar sacs. All these pressures, PAO, PC, PA and PPL, are referenced to the ambient atmospheric pressure P0, which we can conveniently set to 0 for a simplified analysis. Clearly, considering the mechanical and electrical analogies, the pressures PO, PC, PA and PL are denoting voltages in this electrical circuit model. The flows Q, QA and Q minus QA are essentially representing currents, and as discussed earlier, CL and CW, which are the compliances, are essentially nothing but capacitances. Now that we have this electrical circuit model in our hands, we can begin to analyze this and figure out the transfer function, which would essentially relate the input of this given system, the input to the output of this given system. And the input to this given system is clearly the pressure at the airway opening, that is PAO, and the output of the system is the volume flow of air that is delivered to the respiratory system, which will be denoted by Q. So first of all, we apply Kirchhoff's voltage law to the first loop. This would yield PAO minus QRC minus 1 over CS times the integral of Q minus QA times dt is equal to 0. This is essentially because of the fact that P naught has already been set to 0. Furthermore, applying KVL to the second loop yields minus QA times RP minus a 1 over CL times the integral of QA dt minus 1 over CW times integral of QA with respect to t plus 1 over CS times the integral of Q minus QA with respect to t, and that is equal to 0. Now, differentiating the first equation with respect to time yields d by dt of PAO is equal to RC times the d by dt of Q plus 1 over CS times Q minus QA. Differentiating the second equation with respect to time would yield Rp times dQA by dt plus 1 over CL plus 1 over CW plus 1 over CS. This entire thing in brackets times QA is equal to Q over CS. As this particular entire quantity is multiplied by QA, we can replace this by another quantity which we refer to as the total compliance of the respiratory system, denoted by CT, and thus we define 1 over CT to be equal to 1 over CL plus 1 over CW plus 1 over CS, and thus this equation simplifies to yield the following expression: Rp times the d by dt of QA plus QA by CT is equal to Q by CS. Putting equation 3 into equation 5 would yield d by dt of QA equals Q by RPCS minus CS over RPCT times Q by CS plus RC times the d by dt of Q minus the d by dt of PAO. Double differentiating equation 1, which we discussed earlier with respect to time, would yield the second order derivative of PAO with respect to time, that is d2 PAO by dt squared equal to RC times d2Q by dt squared plus 1 over CS times dQ by dt minus 1 over CS times d by dt of QA. Putting equation number 6 into equation number 7 and then simplifying this particular expression would finally yield, using equation 8 again as well, we finally arrived at the simplified form d2 PAO by dt squared plus 1 over RPCT times dPAO by dt is equal to RC times d2Q by dt squared plus 1 over CS plus RC by RPCT times d2 dQ by dt plus 1 over RPCS times 1 over CL plus 1 over CW times Q. Now, this particular differential equation, at first glance, we note that it clearly seems to be quite a difficult expression, a difficult differential equation to solve. Now the Laplace transform comes to our rescue. Using the Laplace transform, this particular differential equation can be converted into quite an easy to simplify algebraic expression. So taking the Laplace transform of both the sides of this particular equation and assuming zero initial conditions now yields s squared times PAO, which is now a function of s, because now all these quantities would be dealt with in the Laplace domain and the complex frequency domain, plus 1 over RPCT times s times PAO of s is equal to RC times s squared Q of s plus 1 over CS plus 1 over RC by RPCT times s times Q of s plus 1 over RPCS times 1 over CL plus 1 over CW times Q of s. Defining the transfer function h of s of the given system as Q of s divided by PAO of s. That is essentially the ratio of the Laplace transform of the output. What was that? As we had defined earlier, the output was the volume flow of air entering the respiratory system Q by the Laplace transform of the input, that is the pressure at the airway opening, and therefore assuming zero initial conditions, h of s is equal to Q of s by PAO of s, and thus we finally get, by further simple algebraic manipulations of this particular equation over here, that h of s is equivalent to s squared plus s over RPCT divided by s squared RC plus 1 over CS plus RC over RPCT times s plus 1 over RPCS times 1 over CL plus 1 over CW. With the expression for the transfer function of the linearized lung mechanics system h of s in our hand, we can now proceed on with the stability analysis of the system. So first of all, we need to figure out as to whether the system that we have built, the model of the linearized lung mechanics system that we built, and we have already figured out its transfer function, is this transfer function corresponding to a stable system or not? In order to do this, we first need to figure out what are the poles and the zeros of this particular transfer function HFS. Now, the zeros of the transfer function can clearly be found out by setting the numerator of the transfer function to 0, while the poles can clearly be figured out by setting the denominator of the transfer function to 0. They would therefore yield that the zeros are S is equal to 0 and minus 1 over RPCT, while the poles would be obtained by solving this particular quadratic equation. They're essentially the solutions to this quadratic equation, and therefore S is equal to minus of K1 plus minus under the root of K1 squared minus 4RC, K2 divided by 2RC are essentially going to be the two poles. In order to get a deeper understanding of our system, let us take a real life example. Let us assume relatively normal lung mechanics of the given patient, of any given patient in general, and therefore the values of the parameters can be taken as RC. This is the central airway resistance, which is equal to 1.5 centimeters H2O seconds per liter. RP, the peripheral airway resistance, is taken to be 0.3 centimeters H2O second per liter. CL, which is the lung compliance, is taken to be 0.2 liter centimeter per H2O. CW, the chest wall compliance, is 0.2 liter centimeter per H2O. CS, the shunt compliance, which is essentially a representation of the central airway compliance, is taken to be 0.005 liter centimeter per H2O. And noting these values for CL, CW, and CS, we can easily define the total compliance CT, which is nothing but the inverse of 1 over CL plus 1 over CW plus 1 over CS, and that yields the value of CT is 1 over 210 liter centimeter per H2O. Plugging in all of these values into the expression for HFS, as we had already defined in the previous slide, would yield the expression for HFS for these normal lung mechanics parameters of the given patient as HFS is equal to S squared plus 700S divided by 1.5 S squared plus 1250 times S plus 6666.67. Again, first start with the stability analysis. As already discussed, zeros can be found out by setting the numerator to 0, and this would yield S is equal to 0 and S is equal to minus 700 as the zeros of HFS. The poles of HFS can easily be computed by solving the quadratic equation which is there in the denominator and in the expression for HFS, and as a result S is equal to minus 5.368 and minus 827.965 are approximately the values of the poles of the transfer function. Furthermore, we note over here that since H of t is right-sided, that is, the impulse response of the given system is right-sided. Why is it right-sided? Because H of t is 0 for all values of t less than 0. Why is this condition given here? We note that this condition is essentially because of the fact that the system represented by the transfer function HFS or even H of t is a causal system. All real life systems are causal in nature, and because of this, the ROC of the causal system H of S would lie to the right of the rightmost pole, and therefore the rightmost pole of the given system is minus 5.368. Clearly minus 5.368 is greater than minus 827.965, and that is why it is the rightmost pole, and therefore the ROC of H of S is going to be given by the real part of S is greater than minus 5.368. As we can clearly see in this particular pole 0 plot, the ROC, which is essentially represented by the shaded region, includes the imaginary axis, right? It includes the imaginary part of S, and as a result of which we note that since the ROC includes the imaginary axis, the system represented by HFS is stable. That is, the model of linearized lung mechanics that we have been considering until now is a stable system. Apart from this stability analysis, another analysis which is of great importance and its usefulness is also quite great is to the pulmonologists who, for example, wish to analyze, infer, and decipher as to how much is the tidal volume, that is, For example, delivered to a patient in an ICU when the peak pressure of the ventilator is set at a prescribed level. For the purpose of a simplified analysis, we consider sinusoidal forcing of the airway opening pressure, PAO, and therefore we consider the case of a sine waveform ventilator. We fix the amplitude of this particular ventilator at 2.5 centimeter H2O, and we analyze the outputs of the given system, that is essentially the resultant airflow versus time, that is Q versus time, and the resultant volume of air that is going to be delivered to the patient versus time. Now this volume of air V is going to be easily obtained by integrating the flow of air. So V is essentially going to be nothing but the integral of Q with respect to time. And we consider this particular model for two cases. Again, we have fixed the amplitude to 2.5 centimeters H2 in both the cases, but the frequency of ventilation is varied. In the first case, considering the fact that the normal respiration rate in a human adult is generally around 12 to 16 breaths per minute. I've used the average of those values, and that would essentially be around 14 breaths per minute, and that has been said as a frequency for case number 1. This would imply in hertz a frequency of 14 by 60 hertz, in radians per second this is equal to 14 by 60 times 2 pi, so this evaluates to 1.467 radians per second. And in case 2, the frequency has been increased to 4 times the frequency in case number 1, which means that almost 4 times, right? We note that the frequency is now set to 60 breaths per minute, and so the frequency in radians per second is approximately 6.283 radians per second. Note over here the usefulness of the transfer function, which we have defined over here. The transfer function enables us to replace the entire electrical circuit system of the linearized lung mechanics by just a simple block in SIMULINK, which is essentially nothing but the transfer function of the given system. So we have PAO, which is the input of the given system, and then as the output we get Q and V. Right, and in the second case, this is again what we are to analyze, with only the frequency of ventilation being changed. The results of which were obtained using the scope were then logged on to the workspace in MATLAB in order to analyze those results in further detail, and these were the results that I had finally obtained. So the first plot essentially tells us as to what is the situation at the low ventilation frequency, right? We noted that the normal respiration rate ventilation frequency of around 14 breaths per minute as compared to the second case is a relatively low value of frequency, and at this particular relatively low value of frequency, we see that this volume waveform, which is the blue waveform over here, is more or less in phase with the waveform of PAO, that is the pressure of the airway opening, which is its black waveform over here, while the waveform of the flow of air, that is the Q waveform, which is a red waveform, essentially we find that it displays a significant lead in phase as compared to the PAO waveform, which is the black waveform. So essentially we note over here that the Q waveform leads in phase the PAO waveform, and when these mechanical quantities are converted into their electrical analogs, we essentially find out that the current leads the voltage. When does that happen? That always happens whenever capacitance affects the dominant, and as a result of which we infer a very important conclusion over here, that the lung mechanics, the linearized lung mechanics that we have been considering until now, is dominated by compliance effects at low frequencies. Again, in this particular case, we can furthermore also see that the tidal volume that is delivered to the patient is what is actually desired as well, right? We know that the peak-to-peak change in the volume, it is about 0.5 liters, that is the tidal volume delivered to the patient, while the flow of air, that is Q, is going to be typically about like it is going to be typically around the peak value of Q is going to be around 0.4 liters per second. Now, in the second case, when we had increased the ventilation frequency to almost 4 times that in case number one, that is, it is approximately 60 breaths per minute, which is approximately 4 times that of 14 breaths per minute, we observed that the frequency of the sinusoid has increased. And now, what is essentially the case is that this Q waveform, that is the red waveform, is now going to be more or less in phase with the PO waveform, which is the black waveform, while the volume waveform, that is the blue waveform, is now going to display a is now essentially displaying over here a significant lag in phase as compared to the PO or the black waveform. That is, V now lags PAO. And when again these mechanical quantities are converted into their electrical analogues, we reason out that now resistive effects are dominant, right? And therefore case 2 highlights the fact that lung mechanics, the linearized lung mechanics that we've been considering until now, is dominated by resistive effects at high frequencies. And in this case, we now also furthermore can note the fact that the peak value of the airflow has now increased, right? We know as compared to the previous case, it has now increased to a value of around 1.1 liters per second, while the volume flow of air, and essentially we are more interested in the tidal volume delivered to the patient, that is the peak to peak change in the volume flow of air delivered to the patient, is now decreased to a value of only about 0.37 liters per second. Thus, this analysis which we have conducted until now is quite insightful because it tells us a very important fact, right? It reveals the frequency dependence of pulmonary resistance and compliance. Thus, with the help of this case study, we've been able to successfully demonstrate and in fact realize in practice the usefulness of the Laplace transform. The Laplace transform has been a crucial a tool of utmost importance in this particular case study, wherein it has essentially enabled us to conduct a thorough stability and transient analysis of the system, and we'd also noticed its usefulness in while deriving the transfer function expression for the given system, and that it had helped us in converting the differential equation, which is quite complex, into an algebraic equation, which is quite easy to solve. Thus, the Laplace transform is indeed a very powerful tool, and in fact, in this particular case of the physiological control system, it yields results which are of great importance to pulmonologists and clinicians alike. Thank you.